Hello, everyone, and thank you for joining us today. We know how busy you are. Everyone on this Zoom session has probably 1,000 things to get through before the end of the business day. So we're flattered that you would choose to spend the next 45 minutes to an hour with us. We have an exciting webinar lined up. We hope you'll find it informative and interesting. And we appreciate you choosing to spend this time with us today. This is part 3 in our installment in a 5-part series looking at graph algorithms for advanced analytics. And this episode in particular, part 3, is focusing on community detection algorithms. My name is David Ronald. I'm the Director of Product Marketing at Tigergraph, and I'm here with my esteemed colleague, Victor Lee, one of the early members of Tigergraph, who's played a pivotal role in shaping the company. And indeed, he is head of product strategy for Tigergraph, head of product strategy, and also developer relations. Victor has a very impressive educational background, in addition to his BS in electrical engineering and computer science from UC Berkeley and an MS in electrical engineering from Stanford. He also has a PhD in computer science from Kent State University, where he focused on graph data mining, and he has more than 20 years in the tech industry. Before we get started, here are a few housekeeping issues. We do want to hear from you. The purpose for this webinar is to share our enthusiasm for graph and to impart the knowledge we have to you to help you benefit from graph analytics. Your phone lines, however, are muted, but we do want to hear from you, and the best way for you to do that is to submit questions. And please feel free to do that anytime using the Q&A tab shown here, and also it's in the panel of the Zoom window. The webinar is being recorded and will be uploaded to our website. You can see the URL there, and that usually happens within just a few hours, same day of the webinar being completed. And we'll also send you an email that has the URL to the webinar, along with some other useful information, and also a copy of the slides too. If you have any issues with Zoom at any point during the webinar, please reach out to us and let us know, and we'll do our very best to remedy them as quickly as possible. So with that, I am going to hand control of the webinar over to Victor, and I'm excited to see what he's going to share with us. Over to you, Victor.
Oops. Thank you, David. Thank you for joining us today. So this is, as you said, part 3 in our 5-part series on graph algorithms. This is a topic that's near and dear to my heart. It's, it combines my love for databases and graphs and algorithms, which were really the motivating topics that led me to graduate school, and then what I chose to focus on, and then I've been so fortunate to be able to make a career out of it. And I hope to share with you some things that I know and how the product Tigergraph is a great platform for running these algorithms. So I'm going to do a recap of parts 1 and 2, which were on path algorithms and centrality algorithms. And then we're going to move on to today's topic, community detection algorithms, really understand what do we mean by that, and then to look at different flavors of community detection. And then finally, I'm going to do some demos using Tigergraph's Graph Studio and running on the cloud using a Tigergraph instance. So I'm going to be using one of our free instances, which means it is the smallest instance that we offer. And even with that small instance, you can do quite a bit. So to review, we talked about what really are we saying when we say we have a graph algorithm. You may know what an algorithm is in general, but there's a set, a family, a collection of really standard algorithms written for doing analysis on graphs that answer sort of basic questions about connected data. And you can think of each algorithm as a tool within a toolkit and or a book within a library. But they're tools. So each one does a function, and you become proficient. You want to learn, what does this one do? What is it good for? And you also realize that to do your larger project, you may want to combine multiple algorithms to do different steps in the building process to build your result to get to the answers, the insight that you want. And so here are just some examples we gave at the beginning in session 1 of different types of practical questions that you might want to answer, from understanding what entity is most centrally located, and what are some practical uses for that question. Well, definitely in delivery logistics, where you're talking about physical location. So that's one possibility. But over here, you can also think about centrality as within a social network or within a commercial network of interact transactions, and their centrality may have to do more with influence or viral spread or impact. So it can be physical distance, or it can be a different type of communication distance. And then that's why centrality is often important. Prior to that, we talked about paths, because anytime you just move within a graph, you are traversing a path. And so knowing how to search and then knowing how to search for paths is fundamental. And then you can start to do these more complex questions. Today, we're going to look at this section in the bottom right about what are natural community groupings. And that can be for understanding risk groups. If say you're in the insurance sector, you want to partition people into different groups so you can set different policies and different rates. Or if you are trying to organize work groups, how do people actually work, as opposed to what's the structure that you've been trying to offer? How do they actually in fact work? Or how are products commonly offered? So we're gonna look at that today. So again, to summarize, for shortest paths, we talked about what are graph algorithms, how to learn to use them. You really need to understand a little bit, make sure you understand what question that particular algorithm is answering and what are some of the pros and cons. And we talked that there are different flavors of shortest path, primarily dealing with whether each link has a weight or not. So if it's unweighted, you're really just counting how many hops. If they're weighted, then you're usually looking for the lowest weight or cheapest path, so to speak. And then we introduced you to the GSQL algorithm library, and we'll be doing more with that today. For centrality, the idea was to think about abstractly the concept of location and travel. And so, we think about one of the fundamental models in a graph is that you think some entity is located somewhere, and then you traverse or walk across the graph, travel across a link to another point. So we used that in path analysis, and we use that for closeness and betweenness also. So if the question you're asking has some idea of central location where you are traveling within the graph, whether it's physical distance or just like how many friend-to-friend relationships do you have to traverse, or how many purchases do you have to make in a sequence to get to something. That's the idea we're talking about here. And again, we talked about closeness centrality and betweenness centrality and page rank. So if you missed that one, you can go back to Graph Gurus 27. It's recorded, and you can see that one. So we're moving down our list. We've covered these previous topics. So today we're looking at clustering and community detection. So here's some slides we actually presented in one of our earlier webinars. And it's talking about a use case in healthcare. So you are looking at a network of providers or prescribers of drugs, and you're looking at the claims that are filed, and you're looking at the ultimate patients or members that are receiving the care. And so you have this complex multi mixed type of entities and mixed type of relationships. And the question we're trying to answer is, which prescribers are the most influential? And the reason why you're interested in is because influence in the sense that other practitioners will tend to follow what they do. That if this prescriber is saying, well, I think this treatment or this drug is appropriate, will they influence the actions of others? And so the first step we do is to run a PageRank analysis. And that's something we talked about at the previous webinar. So let's suppose that we've run our PageRank and we've identified this doctor, Dr. Thomas, as the most influential. And what that means is other practitioners look to him to influence their behavior. And we'll talk later about how we came up with that relationship. How do we understand that referral or authority relationship? But assume that we have that. So we've now found that Dr. Thomas is the most influential. Now we want to look at, well, what is the community around him? Who is he influencing? And here we can use a community detection algorithm by looking at density of connections. And that's really what we're going to talk about today. So that's one example of why you might want to do this. So this, in this case, this could be, who would be running this? This could be an insurance company or a drug manufacturer that wants to understand what is the community of influence. If this is the influential person, who is that person likely to influence? And that could be, you know, the FDA or the drug company or an insurance company all might be interested in that for business reasons, for if you want to introduce a new drug, if you want to understand if is there sufficient coverage. So a lot of interesting questions you could answer from that. So let's talk about community. What is a community? And I spend just a minute, if people want to like type in an answer on the chat line, what is your definition of community? And the reason why I'm asking this is because, you know, with algorithms, there's always sort of a very technical meaning. And the meaning that people might have in English is not necessarily the same meaning that we have here. And again, if you want to be a good user of the algorithm, you want to understand what the technical definition is. So is it, for example, if the entities are people, is it people who live in the same neighborhood? So then physical closeness is important here. And that actually sounds like, well, wasn't that what we kind of talked about with the centrality? And we're not talking about centrality. So what I'd say is, in this case, we're talking about entities which interact with one another in a mutual relationship. And the mutuality is important. So not really looking at hierarchical relationships or, you know, where, you know, someone is supervising another, or definitely person bought a product, where you actually have two different types of entities. Community works when you have the same type of entities and which have some sort of mutual relationship, such as friendship. You know, it can be directed. It can be like, oh, I sent you a message, but there's the idea that you're sort of ignoring the direction in most cases. And it may be that you also don't want to confuse it with similarity. Now, people are in a community often because they have something in common, but that's not what we're going to analyze. We're not going to analyze what they have in common. We're actually just going to analyze their interconnections. So, you know, want to be clear on what we're talking about. So we're analyzing interconnections. So, and the question here, the algorithms really are designed to figure out which ones belong in this group, in this cluster, and which ones don't. Now, in simple case, maybe your objects are labeled already. Like maybe you want to say who is in a Facebook group, and they all had to formally join it. And so at least Facebook certainly knows who is a member and who is not. And so there's really no work to be done. The answer is known. So this is really when the labels aren't there, and you have to just look at the pattern of interconnection to figure out who is in a community. And that's why we talk about natural groupings or organic groupings. You're looking at the activity to lead you to the decision, not on labels. Now, there's sort of two basic ways that you go about this. And there's partitioning, where you take the whole group and you divide it into pieces. And so that every entity belongs to one of the partitions. Nobody's left out. And sometimes you have to make hard choices, like, you know, some of these in the middle here, close to the boundaries of these red dotted lines, you know, really, should I put it on one side or the other? And there's even the question, well, should I have even made a cut here or not? Or is this part and that part close enough together that really should be considered one partition? So those are the decisions you're making when you're partitioning. When you're clustering, you have a freer hand. You are saying, these things are close in some sense, I will put them in a group. And it's okay generally to leave some out. And you are, you know, you're not forced to make a certain number of partitions. Some partitioning algorithms start off with, say, I will make X number, I will make K partitions. And that can really force you to make some decisions that are really not natural. Clustering is a little more organic. So let's look at sort of the range of ways that people have come up with different rules for partitioning. And I see it as a spectrum. And so you can have, I'm using this same data set, 1, 2, 3 examples of the same graph to look at how different rules come up with different clusters. So here we say the rule is you must have one connection to another member. So that's very simple. This follows our intuitive understanding of what is one graph and what is not. So, you know, here, the blue, that is a graph. And the red, that is another graph. And the yellow, that is another graph. Now, if they're all within the same data set, sometimes we say that is one graph, but with 3 components. So each of these connected units, that's a technical term, a component. So there are 3 components to this graph. And so that's what this rule does. It finds the components. And when it's small like this, it's really obvious to do it visually. But when you have 1 million, then you cannot do it visually. You need an algorithm to do it for you. So now we take a step up. We say, well, one connection isn't enough. Let's say I need a certain number, and we call that variable k. And let's say k is 2. If k is 2, then we say, which has at least 2 connections to the other members of the graph? Well, this has only one connection. It only needs one connection. And actually a consequence of the k-core format is that the smallest group is going to be k plus 1, because you need at least k neighbors, right? If there's you, and if you have to have k connections to other people, that means you need k neighbors, so the size of the group has to be at least k plus 1. So for this little box, it works because everybody has one connection, say, you know, to the side, and another one up or down. But this one is left out for the same reason that these are left out. And for this box with the cross, it also works. They actually have 3 connections, but that's more than 2, so they're fine. So there are 2 different k-core components if k is 2. If k were 3, then it would be just the red, right? We'd have to rule out the blue. And if k were 4, we'd have to say nobody qualifies. And then a third option, and which is sort of the extreme in the other end, that here's the most lenient, where you say you only need one connection. And here you say you need every possible connection. And so the red qualifies because there are 4 members here, and each one has a connection to every other member. So that's a clique, or sometimes the vertices form a clique, and the little subgraph there is called a complete graph. So that qualifies. The box no longer qualifies because you can't directly get to the one diagonally across. And while this one didn't satisfy the 2 core requirement, it does satisfy the clique requirement that each one can get to the other. So that's sort of interesting how this one first didn't satisfy that rule, but it satisfied both the one rule and the every other member rule. So 2 key terms to remember: connected component and clique. Now, I said before that direction usually doesn't matter, and that's not always true. In the previous slide, we ignored direction, but this time we are going to consider it. And we actually come up with a new flavor, what we called strongly connected. If strongly connected, you have to be able to get. Now, another way of stating the same rule that you need at least one path, excuse me, one connection, is that you can reach every other member. So if it's undirected, if there's at least one link, you can get from anywhere to anywhere. We apply the same rule here with directed edges. The rule is you have to be able to get from anywhere to anywhere. So realize what we had to do with this little just 2-node little subcomponent. I had to introduce another graph. Another edge going in the opposite direction to let you go in either direction. Now for this one, if it's a box, all going in the same direction, clockwise, we're fine. This one, again, it's clockwise. We throw in some X's. The direction of convince yourself that it doesn't actually matter what direction the diagonal ones are going, as long as you can travel around the box. If I reverse the direction of any one of these edges, then it no longer works. This one, no, you can no longer get from anywhere to anywhere. How do you leave that one there? Same thing, there's no way to arrive at this one, but we are okay for that little triangle. So if we apply the strongly connected component rule, the only thing we get out of this graph is that triangle down there. So we've got now 4 different ways. We got connected component, strongly connected component, we got K-cores, and we have cliques. And we're going to cover one more before we get to our examples. And this is an amazingly popular one. It sort of emerged as maybe the most useful way to do a more flexible relative form of clustering or partitioning. And so the others were looking at very black and white rules. This one is saying, you know, the rules aren't so black and white. What I'm looking for is I want the cluster to feel like it's a cluster. That is, there's more connections within members than going outside. And the way that this is formally stated is they came up with a mathematical measure called modularity. And modularity is defined as the fraction of the edges that are within a group or a cluster minus the expected fraction if those edges were distributed randomly. So each vertex sort of still keeps its same number of connections, but you say, well, those connections could go anywhere. So you kind of roll the dice and say, I'm going to ignore the way the graph is currently drawn, and I'm going to say that you actually could connect anywhere. And that sort of becomes sort of a random perspective of the graph. That's a way of, what if I randomized the clustering? Is the particular clustering I've chosen better than this random? That's where the minus comes in. This is what you have, and then you minus what it would be if we sort of drew the boundaries randomly. And so that gives you a way to compare different options. So for example, I'm comparing which of these 2 cluster boundaries gives a better score. And so what an algorithm does, if the goal is to do community detection by modularity, it evaluates a lot of different options until it finds what it believes is the best option. And it doesn't actually consider every possible option. It's a lot smarter than that. It has techniques for knowing how to work effectively towards the optimal or possibly a near optimal solution. And the reason why it's commonly called Louvain or Louvain is because researchers at a university in Europe, the University of Louvain, they found a particularly efficient way of doing this modularity-based community detection. So I hope that made sense. You don't have to understand the mathematics. It's nice to kind of know what it's doing, and it's important to know that it's finding relative density, and it's searching among many possibilities to find what it thinks is the optimal partitioning or clustering. So again, a really quick look at some other possible applications for community detection before we get to our demo. So marketing or customer analytics. This could be related to the healthcare instance I was talking about, because that could be done for scientific reasons, or it could be done for more business reasons. But you want to see who is talking to whom, or which entity is talking with which entity. And to answer the basic questions of who is being reached, and then so you can understand, do your targeting better. Once you see that there's a natural group, then you can start to look at what are the characteristics of that group. In biosciences, they've been using this a lot. They've actually developed a lot of the improved techniques because they're looking for natural communities of interaction at every level, from all the way down to the molecular and gene level, up to tissues, organisms. So we think of organisms, humans are individual organisms, or at the species level when you're looking at a whole ecosystem. And then financial analytics, when each entity could be a participant in a transaction, or the entities could be transactions or contracts or some other interaction. So for example, this graph is looking at treaty laws and which different nations and other government groups have treaties with one another, to see what are the natural communities of interrelation there. So now we're going to go to the demo. I have a couple introductory comments before I do so. So I've got 3 data sets. The first one is for the drug prescribers that I talked about. It's relatively small with 104 vertices, but it's drawn from a much larger data set. I have a very small one of kangaroos and how they interacted, and we're going to do that because it's a small enough size that we can visually look at the whole graph and talk about how the different communities are being described. And then I have a large one to just so we can look at scalability. This one is about 100,000 vertices and 2.3 million edges. And you can see some are undirected and some are directed. And I'm going to make a quick comment about the data preparation. Data preparation can be an important step for graph algorithms in general. And that's because your vanilla graph algorithm assumes that you have one vertex type and one edge type. That's the way most of them are written. But our real world data sets are often not structured that way. So in the case of our healthcare prescriber data, what we had was we had prescribers who were parties to a claim for some, because there's medical insurance, so you have to submit a claim. And then there was a patient. So patient is party to a claim and for which the service was provided by prescriber. And then if there were multiple such claims, then we looked at the dates of the claims and saw was one date earlier than another. And we made the assumption that if so date 2 comes after date 1, then we assume that there was a referral from prescriber 1 to prescriber 2, and then we inserted an edge into the graph. So the graph originally did not have these referral edges. We inserted them, and I'm going to actually show you that. So as I said, I'm using TigerGraph Cloud. I have a selection of instances. I'm using my free one here. That wasn't the place I want to look. See, where does it show the details? But anyway, it's not that important. So I've got it running here. This schema is in one of our starter kits, so you can get it yourself. Let me see which I should be able to click here to see. that was the information I was looking for. If I were to pick a new create solution, it is this one, the healthcare referral networks, hub, PageRank, and community detection. So you can replicate a lot of what I'm going to be doing here. I've added a couple things, mainly to make the output a little more descriptive. So I will be sending out the details. I will also be sending out the details for the previous 2 webinars I did. I've not published them yet. I apologize. I will be publishing them this week. And then I also added the kangaroo data and the Flickr image data. And so this is showing that each of these is linked to a data source file. Oh, I gotta save that because I just moved them. And I intentionally unloaded the data. I'm going to reload the data for you. It should take about a minute. You can watch the progress here, and you'll see these little bars here should very quickly, you can see some of them are now active, some of them are finished. This one should be finishing in a moment. The one that's going to take the longest is the Flickr edges, because that is the one that has a couple million edges. And you can see the progress in real time. So you can see almost everything is finished except for the Flickr data. Oh, it's done. Okay. And you'll also notice if we go to, there's a referral edges, there are currently none, because remember I said there were no referral edges in the original data. So now I'm going to go to the queries that we have here. And I'm going to run this query, which will create the referral edges. And it's done. And if we go back and look, we now see that we have 417 referral edges as well as reverse referrals. So let's first run PageRank on the, on the referral data. I think those default values look fine. Just so we can see all the results. So it's done. And the results, so this is what it's saying, that these are the top few prescribers or doctors as far as influence. So let's actually take a note of some of those names. Let me see if I can call up a note sheet. I'm just gonna save some things here, say like the top 5 here. And now, let's see, we want to next run, I think, the Louvain. So where was that? It's called algorithm Louvain. And so I've changed it so that I can enter in the vertex types and edge types that I want, because I want to be able to use this for any 3 of the data sets I have. So I have prescriber and referral, and also wants to know the reverse direction. So I'll say reverse referral, and all right. And this is showing some preliminary, like the results while it's running, but now we get to the results. And so these are showing me some clusters. So I have how many? 1, 2, 3, 4, 5, 6, 7, 8 clusters of these. Oh, sorry, 9, because this is showing their sizes. So from smallest to largest. So the largest cluster has 25 members. Most of them so you can see there's one cluster of size 4, one of size 6. There are 2 of size 12. And the question I would like to know is, if I recall it, prescriber 29 was the most influential. And I'd like to know, let's see if I can search. It's a little, or if I visualize it, I probably could see the data, but I'm just trying to see if I can quickly find it this way. Or I could pick one of these others. But actually, the other information I was looking for, the largest one, 7, 2, 3, 5. I'm going to go here, and I want to visualize prescriber. Oh, let me clear the data. Oops, that's not what I want. Actually, that's not what I want. Sorry. I wanted to see the communities around it. Sorry. Let's do this. Prescriber. Let's look at a bunch of them. Thought I cleared that. Try again. Okay. And none of these are the top ones I want. $29. And I want to see the community around this one. So I'm going to see connections to other prescribers. So you can see there are a lot. And you can sort of see why this one might have been judged the most influential. But what I really want to do is see the community ID is 734000324. So if I can color everybody that has that ID. So I can set up a condition for coloring that vertex. Let's make it red. And the condition is if the attribute value, and I should have been smarter in copying that value. That's not, properties. Anyway, 734000324. What I want to do is highlight all the members of that community. So I want to select that type, select a color. So I want to change the color to say red. Set up inequality. If this was the community ID, and if the community ID has this value, hopefully that works. So interestingly, there are relatively few members in the community. There's like a lot of vertices. So interesting choice. It's sometimes not real obvious how the algorithm makes its decisions, but I think when you look at some of the others, you'll see some more interesting results. So I'm going to switch to the kangaroos because that's a really good way to see K-core. So we can actually look at all the kangaroo data quite easily. I happen to know that there's 17 of them. And then we can also just look at all their interconnections. Oops, it's because I need to set that also. So that's the entire graph. It's not that big, but that's the point. We want to be able to see what we have. And the thing in particular I want you to notice is that kangaroo 17 is sort of an outlier, has only one connection to the group, and kangaroo 16 has only two. So those are the two highest ones. There's 17 members, so 16 and 17 have the fewest connections. Now, if you go over and run the K-core algorithm. So first of all, we have a main algorithm and a subquery. So the subquery says it returns a map of, for this K value, it returns the list of all the vertices that are at that K level. So now this algorithm finds just the most dense region. That is, it starts with, if K is equal 1, what is the, so I should explain again. For the subquery, it goes through all the different possible values of K starting with 0, actually. It says, if K is 0, that's the entire graph. If K is 1, is there anybody I have to filter out, and then who's left? If K is 2, is there anybody I have to filter out and who's left? And it keeps going until it's reached the top level. K core induced edges. How come I'm not seeing that? Let's try it again. Oh no, I broke my algorithm. When I was playing with it, I was focusing on the numeric results, and now I don't have my nice visual results. Let me try one more, because what I wanted to show was that what I wanted to show is that at the we start filtering out 17. Remember, kangaroo 17 was the one that had only one connection, so it is in the level 1, and 16 had 2, so it has K2, but then gets filtered out after that. And then there's nothing new at the 3, 4, 5, 6, 7 level. Not until we get to 8 do we find somebody who is at the K equals 8 level. For 9, and then we work our way up to 15. And try this one more time, see if I get a visual result here, but I don't think I do. I think I broke it, sorry. Yeah, this is, so, oh well. If you run Louvain, you again don't get as nice results as you might expect. And that's a good lesson, in that you should not just automatically run an algorithm thinking it's going to solve your problem. They tend to be very data dependent, depending on the nature of, how is your particular data connected. And, data scientists routinely run multiple options, and they use their expertise to help them select, and then a lot of times they actually also have to just try different things. Kangaroo blank 10 10 10 output level. I wonder if I need to make one of these true. I don't think so, but oops. That wasn't good. Okay, let me switch to our big algorithm. So the big one, and I'm going to start, oh, I didn't do strongly connected component. But that only works with directed edges. So I would run strongly connected component with, oh, this one's built in. So this one's kind of hard coded to work on the prescriber data. And so what it's telling us, that we actually get a couple components. One includes everybody, one includes 4, and one includes 1. And I'm not sure, I don't have the most visual. Did I have another version? Oh, enhanced. There we go. I think this has the friendlier output. Yeah, it says, so here's the large component, contains almost everybody. There's another, and then these other components that have just 1 or 2 members. And lastly, I want to go to the large data set and first run K-core on that. Let's run K-core for all levels. And so this one is Flickr. The idea here is they have some 100,000 images, and then the edges are if there is something in the metadata that relates these 2 images. If they have a tag that's the same, or some other information metadata that would relate them, and there's it's actually weighted information, I believe, also that some have stronger links between them than others, but we kind of ignored the weights. And this one does take a little bit longer. I think it takes, oh, it's done. Now, that first line I find really interesting, because what it tells us that for K equals 573, there are 574 members. Remember what I said about the minimum size for a K core is K plus 1? That's here. That means this is a clique. That means for those 574 images, everyone has a direct connection to every other member. That's actually a really interesting result. And it'd be nice to know what those members are. For brevity, I didn't list out all the members, and we could do that, but we just remember they're 100,000. So then we see for, okay, K can increase. I'm going to scroll down to the other end to see what does it look like at the other end of the spectrum. So there's the entire data set, and you don't see any big change in the numbers till here. There's a big jump here when we go from K to K5 to K6. And there's another big jump when you go from K6 to K7. So that's interesting. That sort of says, so 5 is sort of the normal, it's the baseline. Pretty much everybody has 5 things in common with everybody else, or with some member of the community. So you have at least 5 things you have it in common with other people in the community. But then 6 is a threshold. 7 is another big threshold. Once you get to 7, it actually kind of levels off quite a bit. And then it's not until you get to, there's like there, when you get to between 94 and 95, and who knows why that's the case. But so I found that was interesting. So those are the, we can also run, I'll just do one more algorithm. I think it would be worthwhile here. And that would be the connected components. With kangaroos, we saw visually that it was one connected component. Oh, that's the one I could do that for the healthcare also. But since we're running out of time, let's just do this on the big one. Flickr image and Flickr link. And I think that's all I need to say. And so what this is telling me is that there is one component that contains almost everybody, 105,722. And then there is a handful of these other components of very small size, of containing just a couple members. This one has 10 members, but most of them just have 2 or 3 members. That one has 11. So, and that's pretty typical of social graphs, that you find a largest component, and then there's a fairly steep drop off to smaller components. But again, it really depends on the dynamics, how well established the community is. You know, the more established, the more likelihood that eventually you're going to get interconnections. Something else that we didn't talk about is overlapping communities. Now, any one of these algorithms that we've presented will only show you non-overlapping communities. But what you can do is, the reason why they overlap is in the real world is because you're using different criteria. So, well, this community is based on, you know, email, and this community is based on chat. messaging. So you would find those communities using different criteria, and then it's certainly possible that each one is, when you combine them, you see overlapping groups. So we're gonna wrap up here and then go to our questions. So as you can tell, this was not a very, I think you can see this was not a marketing presentation. You know, I'm very much, I said, you know, this took me back to my grad school days. I really like playing with algorithms, but I hope I showed you how in a work setting, doing data science, you can find out a lot with these algorithms. And certainly then you can find out what works for you and really productize it into an application. Excuse me. And why the GraphSQL algorithm library is so appropriate here. As I didn't have time to show you, I'll do this in the notes when I publish, but I did tweak each of the algorithms primarily because I wanted the output in a more presentable way. So, you know, the core algorithm doesn't really change most of the time. I did tweak some of them because we now have some capability where you can accept the vertex type or attribute type as a parameter. And rather than having them hard coded to the prescriber data set, I wanted to be able to run the algorithms for the inputs of my choice. So that's another tweak I made. You can update the graph results. So you're not just reading the data, you can actually write to the graph also. And I talked about modifying. I could have shown you how the K-core algorithm I literally implemented this week. I read a paper, I looked at the pseudocode, and I almost line for line translated it into GSQL. And I'd be happy to point that out in the notes how I did that. And so you could do the same. Once you just take you maybe a couple days to become familiar with GSQL, and you could do the same thing. And really, in particular, I looked for algorithms that do parallel processing. We can implement sequential execution. It's fine, but it's going to be slower. With the TigerGraph platform, you really want to take advantage of the parallel processing. So, you know, when I looked for a K-core or a clique algorithm, I looked for parallel processing algorithms. And that's, you know, TigerGraph is capable of executing that. I'm not familiar with any other platform that's any other graph database that's going to do the same thing. So to summarize, community detection algorithms look at connectedness to decide the boundaries for the clusters. I think communities are clusters, not really partitions. There certainly are some algorithms that are more partition based and that are used. So, and it depends on what you consider. You know, if a cluster can have just one member, okay, that's, you know, that's a partition, whatever. And I've talked about different rules we have for defining communities, black and white rules, like you must have at least one connection, or you must be connected to everybody, or you must have K connections, they must be directed. And finally, we talked about Louvain, which has become very popular because how it looks at relative density. And in the real world, relative density is often the most appropriate measure. And then I talked about some pre or post-processing steps you can take, such as data preparation, running PageRank beforehand to find out centrality. So, and that's just another part of this aspect of really, you often want to combine algorithms to, each one is doing one step in your overall process. And once you become familiar with them, you can do some really cool things. So we're going to turn to our Q&A, invite David back, and maybe he can help me with any questions that people out in the audience have had.
Sounds good. I'm back. Thanks, Victor. That was an especially fluent demonstration, and certainly one of the most interesting webinars I think we've done, and probably the most interesting in this series. So my challenge to you would be to make episode 4 even better than this one. Anyway, in the interest of time, we'll go through just a couple of questions because I know we're getting close to the top of the hour. One question we've had, which I think is a bit tongue-in-cheek, is what did what did Kangaroo 17 do to the community to be so unpopular?
I wish I knew. I'd have to
Okay.
go back to the research paper to find it.
Okay. Another question that we've had is, what if I want an algorithm that is not in your library?
That's a great question. As I mentioned, that I implemented K-Core on Tuesday or yesterday, Monday or Tuesday of this week, because I was familiar with it. I wanted it to be in the library, and I just put it in. So there's the same thing. If you know, we're a little more familiar with GSQL than most of you, I would like to think. So if there's one that you would like to see, drop us a line. We have a lot of ways that you can reach out to us. In fact, I wonder if we have that listed here. We have a developer forum, but we also have, we're expanding the number of ways you can reach us through our community outreach. We'd be happy to see if we can try to implement it for you, or if you want to do it as a learning exercise, we can give you tips and work with you to implement it.
Sounds good. Another question, looks like there might be a typo in this. Will their algorithms run on a distributed graph? Will their algorithms run on a distributed graph?
Yes. So, you know, one of the benefits of the Tiger Graph platform is that we are a distributed database. That means you can run the same software on multiple servers and load one set of data that's automatically spread across the multiple servers you have. And you run queries the same way automatically, that you don't have to write the query any differently because the data is distributed. That's all taken care of by the Tiger Graph system. So, you know, when your system administrator sets up, you've got these multiple servers. You, as the developer, don't need to worry about that. Any of the algorithms I showed today could have been run on a distributed system exactly the same way as they are now. And the benefit of that is that you get more computational power. You can process a larger amount of data, or you can process the same amount of data with greater speed.
Okay, great. Another question, how does the Tiger Graph algorithm library compare to libraries from other graph database companies?
Well, I won't claim to be an expert about what the other companies offer. As a product manager, I am responsible for keeping tabs on some of them. I will, some things I would suggest that you look at, and differences that I believe there are. I think ours is actually unique in that we truly run within the database rather than exporting the algorithm to sort of run on the side. In some cases, the user has to actually export the data, and so it's not really running in the database. The other thing I would say is three differences actually running in the database. User modifiable. So in many cases, it is a closed, pre-compiled function. You just call the function and you can't see it into it, you can't modify it. And the third is that we are executed with parallel processing, which greatly enhances the performance for large data sets. So those are the differences I'm aware of.
Okay, awesome. I think in the interest of time, Victor, why don't we wrap up the webinar? As Victor mentioned, we are trying to make it easier for people to get in touch by having a presence in more places and providing more avenues for people to reach out to us. And on top of that, we're providing additional resources. Tiger Graph Cloud is a fantastic way to get started with our software, which is one of the leading graph database analytics software on the market. Obviously we're biased. We would say it is the best, but undoubtedly it's one off. What's especially appealing about Tiger Graph Cloud is it takes just a few minutes to open an account, typically about 5 or 6 minutes to open an account. There's a free tier, so it doesn't cost you anything. If you want to have access to a single solution, and if you want to have access to more, you can put in, you can give us a credit card number, and you have $25 in free credit, which is about 10 hours or so of experimenting with the product. And in addition, a feature which I think is especially appealing is it's pre-populated with 18 starter kits. So a newbie isn't trying to figure out, what to do first. We're making it much easy, or very easy, for people to get started. Additionally, we have our test drive online demonstrations, which you can access at that URL shown there. You can also download the developer edition and use that. And we have a variety of Guru scripts available, all intended to help you get started quicker. Okay, so these webinars, which you'll have noticed, are called our Graph Gurus webinars. We have started bringing these or making these in-person events, which we call Graph Gurus Comes to You. We have one later this month, next week, in fact, in Atlanta, Charlotte, London, San Francisco, and a variety of other places. And you can view all of the events that we have on our calendar at that URL shown there. And even better, if you wanted us to come to a location close to you, you can reach out to us, let us know, and we'll be happy to work with you on the logistics. Our next webinar is next week, Wednesday. And in fact, there's a typo there, a couple of typos. The time is 8 a.m. Yep, thank you, Victor. Our webinars are typically at 11 a.m. Pacific, but next week, this webinar is at 11 a.m., 4 p.m. UK time. This is going to be managed by one of our very capable SEs in Europe, and it came at the request of some people in Europe for a webinar that would be at a slightly more convenient time for European audiences. And that's why we spell optimization with an S. That is not a typo. This is something that's targeted towards our European audiences. We'd love to have you attend, but please do notice the time difference, 8 a.m. next week, Wednesday. And that brings us to the end of this webinar. Again, I wanted to compliment my colleague, Victor Lee, for an especially fluent webinar. It's one of the most interesting webinars we've done. I've learned a lot. And I wanted to thank you, the audience, for staying with us to the end. We know you have a lot of things you have to get done today, and we're very pleased, honored, and flattered that you stayed with us. We hope you found this webinar interesting and insightful. Reach out to us if you have comments or suggestions. We'd love to hear from you, and we look forward to seeing you at a webinar in the near future. Thank you.